Today we're diving into one of the most mind-bending things in all of physics, superconductivity. It's a world where the normal rules of electricity just kind of break down, and what's left behind looks an awful lot like magic. So let's just jump right in.
Okay, I want you to just picture this for a second. What if you could run an electrical current through a wire, turn off the power, and have that current, well, just keep going? Not for a minute, not for an hour, but for years, decades, maybe even longer. And look, this isn't science fiction. It's the core promise of superconductivity. And if you want to see what that magic looks like, this is it. I bet you've seen this classic demonstration. This is no trick. That puck is just floating, completely stable, just hanging there, locked in place by some kind of invisible force. It's an effect so strange it seems to defy gravity itself. So today, we're going to pull back the curtain and see exactly how this works.
So yeah, this magic, it's not actually magic. It's all about a really unique set of physical properties that create, well, what is basically a perfect conductor.
All right, so here's the key thing you gotta understand. Superconductivity is like a package deal. It's not just one thing, but two key things happening at once. First off, its electrical resistance just vanishes. Gone. And I don't mean close to zero, I mean zero. And second, the material literally kicks out any magnetic fields from inside itself. But, and this is a big but, this whole show only starts when you get it colder than a very specific critical temperature. To really get a feel for this, think about a normal wire, like in your wall. The electrons flowing through it are like people trying to sprint through a super crowded, shaking hallway, right? They're constantly bumping into things, into the atoms of the wire itself, and all that bumping creates heat. That's resistance. But in a superconductor, it's totally different. The electrons pair up and they start gliding through that same hallway like professional dancers. They don't bump into anything, they just flow. Forever. It's like a frictionless superfluid of charge. And when I say forever, I'm not really exaggerating. It's honestly hard to wrap your head around this. Get this. In a real experiment, scientists started a current in a superconducting loop, and that current, with no power source, kept flowing for over 28 years. 28 years. That's the kind of insane power we're talking about with zero resistance.
So where did all this come from? How do we even stumble upon something so weird? Well, the story starts more than 100 years ago, with a quest to make things colder than they'd ever been before. You know, the whole picture didn't just appear overnight. It all kicked off back in 1911. A guy named Heike Kamerlingh Onnes was playing around with super cold mercury, and bam, he saw its resistance completely disappear at 4.2 Kelvin. Then, fast forward 22 years, two other scientists, Missner and Oxenfeld, they find the other half of the puzzle, that weird thing where it kicks out magnetic fields. But nobody really knew why it was all happening until 1957. That's when three geniuses, Bardeen, Cooper, and Schrieffer, came up with the BCS theory and finally explained the whole thing. They even got a Nobel Prize for it, and rightly so.
And that theory, BCS theory, is where things get, well, they get really weird, but in the best way possible. The secret isn't in the physics of our everyday world. It's deep down in the strange rules of the quantum realm. It's like a quantum dance.
Okay, stick with me here. Normally, electrons are like grumpy little particles. They all have the same negative charge, so they want nothing to do with each other. They push each other away. But when you get things super, super cold, the structure of the material itself, the atomic lattice, starts acting like a matchmaker. See, as one electron zips by, it pulls on the positive atoms in the lattice, creating this little vibration, a phonon. And that little positive ripple is just enough to attract a second electron from a distance. And boom, you've got a Cooper pair. These pairs are now linked, acting like one single thing. And this pair fluid can just glide right through the material without being scattered or bumping into anything. No collisions means no friction, and no friction means, you guessed it, zero resistance.
So for like 70 years, this was all super cool, but also super impractical. I mean, you needed this crazy expensive liquid helium to make it work, so it was basically a laboratory curiosity. But then the 1980s happened, and a revolution completely changed the game. So in 1986, you've got these two researchers at IBM, Bednorz and Mueller, and they're messing around with these brittle ceramic materials, you know, the kind of stuff you'd normally think of as an insulator, not a conductor. And they find superconductivity in it at 35 Kelvin. Now, at the time, that temperature was thought to be impossible. It just shattered all the existing theories, and they snapped up a Nobel Prize for it almost immediately. It was that big a deal.
That discovery just blew the doors wide open. Pretty soon after, another material, a compound called YbCO, was found and it became a superconductor at an incredible 92 Kelvin. And that number, 92K, it isn't just a little bit higher, it was a monumental leap forward. So why? What's so special about that particular temperature?
Well, here's why that number changed everything. Remember that old school stuff? To get down to 4 Kelvin, you had to use liquid helium. It's super expensive, it's pretty rare, and it's a real pain to work with. But 92 Kelvin is warmer than 77 Kelvin. And 77 Kelvin just happens to be the boiling point of liquid nitrogen. And liquid nitrogen, it's everywhere. It's cheap. We're talking about the same price as a gallon of milk. All of a sudden, this amazing technology wasn't just for elite physics labs anymore.
And that breakthrough, that's what paved the way for the real-world applications we're starting to see. It connects this really wild physics to technologies that are already part of our world and honestly are going to define our future.
In fact, there's a good chance many of you have actually been inside a machine that uses this tech without even realizing it. See that giant 80% chunk of the pie? Yep, that's MRI machines. Those incredibly powerful magnets they need to see inside your body, the only way to make them that strong and stable is with wires made out of superconductors.
But MRIs are really just the tip of the iceberg. The stuff that's coming next, it's absolutely transformative. We're talking about the huge steering magnets and particle accelerators like the Large Hadron Collider. Or how about super-fast maglev trains that literally float silently above the tracks? Imagine a power grid that doesn't waste a single watt of energy between the power plant and your home, or the tech that could be the key to building quantum computers and finally cracking fusion power. So, all of this is leading to the ultimate holy grail for physicists, a room temperature superconductor, a material that can do all this amazing stuff without any cooling at all. I mean, think about it. It would change literally everything from the computer in your pocket to our global energy grid. So I'll leave you with this final, massive question. When we finally find it, and we will find it, what's the first world-changing thing we're going to build with it?